And now, it's my pleasure to invite our second resource person of the evening, Dr. B. Sridhar sir. Before I could invite him, I request Dr. A. Chandrababu, the coordinator of this FDP, to introduce Dr. B. Sridhar. Dr. Chandra sir, please take the stage and introduce our esteemed speaker to the audience.
Yeah, good evening. I am delighted to have the opportunity to share the profile of today's resource person. Dr. B. Sridhar Babu is a distinguished professor in the Department of Mechanical Engineering with an impressive academic and research career spanning 22 years. Holding an MTech in Advanced Manufacturing Systems from JNTU Hyderabad and a PhD in Mechanical Engineering from the same university, he has established himself as a prominent academic and researcher. A fellow of the Institution of Engineers, Kolkata, and an active member of professional bodies like ISTE, IAE-NG, and SEAE India, Dr. Babu has made significant contributions to the field of engineering. His academic portfolio is marked by 65 published papers in national and international journals and conferences, 10 authored textbooks, and mentorship of over 75 BTech and MTech projects. Specializing in advanced manufacturing systems, contact machines, additive manufacturing, and advanced materials, he also serves as an academic and guest editor of multiple prestigious journals and conferences, including Handway Publications, Materials Today, and Springer. Currently serving as a professor in Malad Engineering College, Dr. Babu brings a wealth of expertise and a robust research background to his academic role. And now, without further delay, I hand over the session to Dr. Sridhar. We are excited to hear from you, sir. Please, over to you, sir.
Good evening, everyone. So already my introduction is just given by one of the coordinator of the FDP. So again, myself, Dr. B. Sridhar Babu, professor in Malad Engineering College, Hyderabad. My main area of research is material science. So today I'm going to deliver a lecture on nanotechnology and nanomaterials in semiconductor design. So in this topic, I'm going to cover what is nanotechnology, what is the role of nanotechnology in the semiconductors design, and also I'm going to give brief introduction about the nanomaterials. What are nanomaterials? What are the types of nanomaterials? What is the importance of nanomaterials? And what are the properties of nanomaterials? How we are going to find out the properties of materials? How these nanomaterial properties influencing the semiconductor design? And what is the role of this nanotechnology and nanomaterials in this design? Semiconductor design, and what are the application of this nanotechnology, nanomaterials in the different areas. So that I'm going to cover in this brief talk on this topic. Coming to the introduction part of nanotechnology. As you know, nowadays nanotechnology and nanomaterials are playing a major role in all fields, including engineering, health, food, and environment. In many areas, this nanotechnology word is playing a major role. So what is this nanotechnology actually? So this nanotechnology is nothing but science of manipulating atoms and molecules to make advanced nanomaterial. This is one of the definition of nanotechnology, but there are many definitions for nanotechnology. Actually, we can say that it's a technology which is used to fabricate or study or characterize the nanomaterials or nano devices, we can say. So coming to the atoms and molecules. So in this nanotechnology, we come across with atoms and molecules generally, because as you know, atom is the smallest particle in the universe. This nano stands for small. I think nano is a Greek word, which the meaning of this Greek word is small. So atoms are the very smallest particle in the universe. So that's why we come across with the atoms and molecules in this nanotechnology. As you know, you studied about the atoms, molecules, electrons, protons, nucleus, orbits, and the basic fundamentals of atomic structure in the school standard level, that is 8th and 9th and 10th. So according to the basic concepts of atomic structure, we can define atom as it's a building block of all matter. In a matter, the smallest particle is nothing but an atom. If we combine the atoms with other atoms, it forms a molecule. So size of the molecule is a little bit more compared to the atom, but we cannot atoms cannot be broken into smaller pieces by any ordinary chemical process. That atom cannot be um, divided or broken into pieces because it's the smallest particle. Further, we cannot divide the atom, right? So coming to the definition of molecule is a group of two or more atoms forming the smallest identifiable unit that retains the composition and chemical properties of that substance. So group of two or three or four atoms forms a molecules. And coming to the advanced nanomaterials, new materials with enhanced properties designed to provide superior performance is nothing but advanced nanomaterials. There are many number of nanomaterials, advanced nanomaterials available now that we'll discuss in the next slide. But these are the very advanced materials and which are having very great superior properties, and they perform very nicely with the high performance. So here we can see another definition of nanotechnology is the understanding and the manipulation of matter in sizes ranging from approximately 1 to 100 nanometers, where unique phenomena enable new applications. Yes, this is very important definition of this nanotechnology. Actually, nano is nothing but 1 billionth of meter. That we'll see in the next slide. Actually, in the nanotechnology, we'll come across the materials and devices which are in the range of 100 to 1 to 100 nanometers length scales. Okay. And if you see another definition of nanotechnology, it's an emerging interdisciplinary. Nanotechnology is interdisciplinary. Mechanical engineers can apply the nanotechnology, electrical and electronics, computer science and physics, chemistry. So it's a nanotechnology interdisciplinary field involving the physics, chemistry, biology, engineering, material science, and computing. Nanotechnology comprises of all these sciences, physics. So majorly the nanotechnology starts with physics, quantum physics. I think all of you studied the quantum physics in the intermediate level and engineering first year physics. That I'm going to cover a little bit about the quantum physics also in this talk. So coming to nano, actually what is this in the nanotechnology world? What is this nano? Nano is the millionth of millimeter or a billionth of meter. See, the prefixes of small quantities, milli, right? Micro and nano. Milli is nothing but 10 to the power of minus 3, and micro is nothing but 10 to the power of minus 6, and nano is nothing but 10 to the power of minus 9. So here nano is nothing but millionth of a millimeter or a billionth of a meter. That is 1 nanometer is equal to 10 to the power of minus 9 meters. Suppose if you take a 1 meter wire, if you divide that wire into 100 crores parts, small parts, then that small parts comes under 1 nanometer. The length of the small part is nothing but 1 nanometer. 100 crores. If you divide a 1 meter into 1 meter wire into 100 crores parts, then that small part, one small part length is nothing but 1 nanometer. And if we define the nano with respect to the atom is about 0.1 nanometer. The size of the atom is 0.1 nanometer, and 10 atoms, if we keep side by side, it make up 1 nanometer. So if you arrange the atom side by side, 10 atoms, then the length of the atoms, the size of the atoms becomes 1 nanometer. Now, that means there's a very small unit, nanometer, that you might be understood with this. So if you see the water, water atom is a 10 to the power of minus 1 nanometers. Glucose atom is 1 nanometer. Antibody. So here you can see the sizes of each antibody: 10 nanometers, virus 10 square nanometers, bacteria 10 to the power of 3000 nanometers, and cancer cell 10 to the power of 4. So, and here you can see one example of human hair. The human hair diameter is 50,000 to 1 lakh nanometer in diameter. See, our hair diameter is 50,000 to 1 lakh nanometer diameter. But in nanotechnology, we come across only 1 nanometer to 100 nanometer scale range only. That is nothing but nanotechnology. That means you can understand, you can imagine the size of the nanomaterial, nanoparticle, you can say. Okay, so there are many devices in the nano range: nanoprons, dendrimides, nanotubes, quantum dots, and nanoshells. These are all under nanoscale range particle. You'll understand what is this, all these things in the next slides. Coming to the nanomaterials, this is very, very important. So nanomaterials, if the materials sizes are in the range of 1 to 100 nanometers in at least in one dimension, then that material is called nanomaterial. I'm repeating this, the definition of the nanomaterial. If any, see, three-dimensional object will have 3 dimensions: length, breadth, and height. If any dimension of the object or material is in the nano range is nothing but what? 1 to 100 nanometers. If any one dimension of the device or material in the range of 1 to 100 nanometers, then that material is called nanomaterial. So the material, any one dimension should be in the nanoscale range, that is 1 to 100 nanometers, then it is called nanomaterials. So based on many things, the nanomaterials are classified, but based on the size of the nanomaterial, the dimension of the nanomaterials are classified into 1, 2, 3, 4 types. The first one is zero-dimensional nanomaterial, and the second one is one-dimensional nanomaterials, and third one is three-dimensional nanomaterials. Now, if you see the definition of 0D nanomaterial, that is nothing but zero-dimensional nanomaterial. If all the 3 dimensions are in the nanoscale range, if all the 3, suppose the length, breadth, and height, these 3 dimensions are in the nanoscale range, then that material is called zero-dimensional nanomaterials. So the best examples of this 0D nanomaterials are nanoparticles, colloids, and quantum dots. We'll discuss about the nanoparticles and quantum dots in the next slides. And the one-dimensional nanometer, one dimension beyond the nanoscale and 2 other dimensions in the nanoscale range. If any 2 dimensions are in the nanoscale range, then suppose if height is not in the nanoscale range and the remaining 2 dimensions are in the nanoscale, then that material is called one-dimensional nanomaterial. Okay, if any 2 of the dimensions are in the nanoscale range, then the material is called what? One-dimensional nanomaterial. And the best examples for the nanomaterials are nanowires. I think you might seen the images of nanowires, nanorods, and many of you working on these characterization of these materials and the performance of materials, and also you might be working on the techniques which are used to characterize these materials, or some of the mechanical engineers working on the nanocomposites, In the composite, generally we use these nanoparticles and carbon nanotubes and everything. So these nanowires, nanorods, nanotubes, biopolymers, all these are comes under one-dimensional nanomaterials. Coming to the next type of nanomaterial, that is two-dimensional nanomaterial. Any two dimension can be outside of the nanoscale and one dimension in the nanoscale. See, out of three dimensions, if one dimension only in the nanoscale range, then it is comes under two-dimensional nanomaterial. The examples are plate-like shapes, nano layers, surface coatings, and thin films. I think you might be knowing the application of coatings to resist the abrasion and wear. Generally, in the mechanical parts, we apply the coatings. If the thickness of the film is nano range, see, if you assume, if you imagine a layer, then if the thickness, the dimension of the thickness is nano range and length and width are not in the nanoscale range, then that layer is called what? Nano layer or nano film or nano coating, we call it as. So the best example for the 2D nanomaterial is thin films and surface coatings. Many people are working on thin coatings and surface coatings, nano layers. There are many techniques available to coat the nano layers on the machine parts or any other parts, and what are the techniques we use to coat the layers on the parts. That also very important topic in the nanotechnology. So many people are working on this. Many people got the PhDs in this nanotechnology area. So nowadays everybody is showing interest in nanotechnology and nanoscience, nanomaterials. Coming to the last one, that is three-dimensional nanomaterial. Or if all the three materials can be outside of the nanoscale, made of nanomaterials, then it is called three-dimensional nano. With this, you might be understood the meaning of the three-dimensional nanomaterials. If the three dimensions of the material is not in the nanoscale range, then it is called a three-dimensional nanoscale nanomaterial. So here you can see the examples of three-dimensional nanomaterial. Nanoparticle dispersions, nanowire, nanotube bundles, multiple nano layers. And you can see the images of here zero-dimension nanoparticles and one-dimensional nanowire. This is about the basic the classification of nanomaterials based on the dimensions. Okay, so I'm not going to cover the different types of nanomaterials, right? So this so if you see the a gallery of photos of nanomaterials, here in the left side, image A and B shows the zero-dimensional nanoparticles, that is single particle atom. There's quantum dots you can see, and in the top of the slide you can see the composite material image, and at the bottom you can see the coated layer nanoparticles. You can see all these comes under the zero quantum dots. So here you can see the images of different nanomaterials. So nanowire, nanorods, nanotubes. You can see the images of these nanomaterials in this slide. Okay. Now coming to the history of these nanomaterials. The Roman glaciers, 4th century, made a Lycurgus cup of soda lime glass dyed with aurum and argentinum nanoparticles that appears green in reflecting light and red transmitting light. See, If you see the properties of nanoparticles, you will find many very fascinating, very dynamic properties you will find for the nanoparticles. So this is one of the important property of nanoparticles. When you coat a body or an object with a nanoparticle, then with respect to the size of the particle, the color will appear. The color changes based on the size of the particle. You will study about the effect of size on the properties in the next slides. But see here, actually, in this image you can see the colors, green color and red color. So that material is same, but they're showing different colors. Why? Because of the coating of nanomaterials with different sizes. So this was applied in the 4th century only. So this technology was there in the 4th century. In the Middle Ages, multicolored windows panels of churches are stained with nanoparticles of various metals. So at that time only these nanoparticles are used in painting of the windows and multicolor windows. So that was observed. And this is very important. The third one, in the 16th and 17th centuries, an extremely strong yet flexible Damascus sword was made using carbon nanotubes and iron carbide Fe3C nanowires. They were unusual strong yet flexible enough to bend from hilt to staff. See, at that time only in the 16th and 17th century, carbon nanotubes were used to manufacture the swords of the warriors. So actually in 2010, when I was in IIT Chennai, one researcher is doing research on this Akbar and Babur time swords. Actually, they collected some sword material from the Mughal emperors, and they are studying about the nanoparticles in the IIT Chennai. I wondered by seeing this. I wondered at that time in 2010 when I was doing my PhD. And also, I think all of you know Talapatra Gandalu, Telugu, we call them as Talapatra Gandalu. Up to now, they are existing. Why? Because of these nanoparticles only. They are coated with nanoparticles. On the leaves of the plants, they use it to coat the nanoparticles. Because of that, they are existing up to now. So at that time only, they used the nanoparticle. So a lot of research is going on now on the nanoparticles and nanotechnology. And coming to the few more points on history. In 1857, Michael Faraday attributed the color of stained glass windows to the presence of metallic nanoparticles. He prepared red gold nanoparticles stored at the Royal Institution in London. Right, actually gold, actually in the what I think all of you know the color of gold. Gold color is if the size of the gold is a bulk, right? If it is not, the size is not in the nanoscale range, then it appears in yellow color. Actually, gold looks like yellow when it is a bulk material. But when you make it into a nano size particle, when you divide that gold into a nano size, then that nanoparticle looks like a red color. So it appears in red color. So that we'll see the reasons why when the size decreases, why the colors are changing. That we'll see. It's nothing but physics. The frequency, the emitting light will vary. The frequency of emitting wave will vary with respect to the size. I think all of you know. I am going to cover the energy bands, electrons falls from one band to another band. What is the frequency? When the frequency changes, how it appears. All these things you'll study in the quantum physics. Actually, if you are perfect in quantum physics, you will understand very easily, right? So in 1908, Gimai explained the change in the color of glasses by the size of the metal particles scattered in glasses. That's what I told you. When the size of the particle changes, then particle color changes. So in 08 year only, this GMI explained the change in the color of glasses by the size of the. You can see in this image. You can, if you see the sizes, it's tinted. Here, this color is appearing because of 20 nanometer size. When the particle size is 30 nanometers, this is the appearance of the particle. When the size of the nanoparticle is 40 nanometers, this is the color it is getting. When the particle size is 60 nanometers, this is the size the particles are getting. So based on the sizes, the materials appears in different colors. All right. So that will study why these this the color is changing due to this size. We'll see next in the next slides. R.A. Zygmundi, first decade of the 20th century, studied the optical properties of gold and other nanoparticles and received the Nobel Prize in Chemistry in 1926. In the 1926 itself, the Zygmundi studied the optical properties of this gold and other nanoparticles. Initially, most of the people concentrate on the gold particle because of this dynamic optical properties. And this person got the Nobel Prize in Chemistry in 1926. Great personalities who are related to the nanomaterials we'll see now. In 1959, the American physicist Richard Feynman, in his famous speech, "There is a plenty of room at the bottom," gave an idea of nanotechnologies, foresaw the possibilities and potentials of nanotechnologies. Denser computer circuit is following the doctor. See, this was actually this is the basis for the nanotechnology. In 1959 itself, the Richard Feynman told in his speech that there is a plenty of room at the bottom. Bottom is nothing but at the smaller size. Smaller bottom. Bottom means small size. There is a plenty of room, plenty of movement, or we can say plenty of scope is there at the bottom. Bottom means small size. So Gordon E. Moore, this is very, very important law. Actually, the nanotechnology concepts started from this Moore law only. Gordon E. Moore, 1965, is a co-founder of Intel Corporation, made an amazing prediction. It's not a law actually, it's a prediction observation. We can say that it's an observation from the experience what he faced in the industry in the Intel Corporation. The number of transistors on a chip of a given area will double every 1.5 years. So what is saying? The number of, this is the basis of the nanotechnology actually. You can see the graph of Moore's law with respect to the transistor counts and year the processor was introduced. So for every 1.5 years, the number of the transistors are increasing. That means a IC, integrated circuits. So that was he observed. The size of the transistor reduced 2 times every year. That's what. When the number of transistors increase in a integrated circuit, when the size of the transistor decreases, then number of transistors will increase on a integrated circuits. So that means what? The devices are the size of the device are reducing gradually every year. That is the meaning of it actually. His prediction indicated that today's transistor would be 1 to 2 nanometers in size. You can imagine the size of the transistor, 1 to 2 nanometers. This is true, but we have some problems there. Everywhere there is a, see, in any invention, definitely problems, flaws will be there, and some assumptions will be there. So when the size increases, what happens? The computing power improves and the energy levels required is very low. That is the major advantage of the nanoscale range. This is very important. Moore's law is a very basis for the nanotechnology. And the next one is the Nobel Prize in Physics in 2010 has been awarded to Andre Geim and Konstantin Novoselov for groundbreaking experiments regarding the two-dimensional material graphene. So this person studied about the two-dimensional material graphene. Now coming to the bulk to nano, what happens? This is very, very interesting. When the material changes its size from bulk to nano, it behaves differently. I think you might be knowing, when the size of the material changes from meters to nanometers, then the material behaves differently under certain conditions. Its properties totally changes when the size of the material changes to nano level. Then its properties totally changes. For example, if you see the zinc oxide ZNO optical properties, the large ZNO particles block UV light, scattered visible light, and appear white. So this is for what? Large ZNO particles. I'm talking about here large ZNO particle. If you see the nano-sized ZNO particles, block UV radiation, not light, UV radiation, are so small compared to the wavelength of visible light that they do not scatter and it appears transparent. So application of sunscreen we used to we apply on the face to avoid the ultraviolet radiation, right? Now in the mechanical and electrical properties also, majorly we are using carbon nanotubes, CNT, we call them as CNT. CNT are long, thin cylindrical of carbon. They are 100 times stronger than steels. In composite materials now, in the lightweight structures, we are applying the nanotubes. They are very strong, stronger than steels. The bond between the carbon atoms will be very high in carbon nanotubes. It's a very interesting topic. If you see the chemistry of the carbon nanotubes, you'll feel very excited and you'll feel happy. You will get interest on the study. Very flexible and have unique electrical properties because of the energy band gap variation. You'll find the very electrical properties of changes with diameter, twist, and number of walls. According to their electrical behavior, they can conducting and semiconducting. See, according to their electrical behavior, we can say conductor material, non-conductor semiconductor material, and insulators. This depends upon the energy gap between the energy bands that you will might be studied in the semiconductors chapter of the BTech first year. Right. Little bit we'll focus on the quantum physics. What is quantum physics? And because we are mainly focused on quantum dots, which are majorly used in the electronic application of applications. So quantum, to explain the effect of quantum size, we have to make small leap and imagine what quantum physics is dealing with. So to understand the size of quantum size effects, we need to understand the quantum physics. So, we studied the classical physics, and after that, we moved to the quantum physics. Quantum physics is a set of laws that explain observations of the tiny building blocks related to atoms of all the matters. And the quantum world should be able to explain the classical world we live in, present our life. To understand the quantum world, we need to understand and believe in the equivalence of a single atom and an electromagnetic world. As I told you already in the first slide itself, we studied the atomic structure in the 8th and 9th and 10th classes. So that we are going to a little bit focus. We are going to focus on those concepts here related to the atomic structure. If you have some idea about this, then you can understand what is energy band and what is energy gap and how the materials varies the properties with respect to the energy gap, energy band that we'll see now. So as you know, Rutherford classified model of atom in the 8th class, I think atomic structure, you studied this. Observation shows that the atom is basically empty space with a dense central positively charged structure in the center. The electrons exist outside this nucleus and revolve around it like planet around the sun. This problem with the classical model, the electron has negative charge and revolves around the central positive particle, the nucleus of the charge therefore has the magnetic field. So these are the observations of Rutherford model. sorry, this is because of this observation does not match the theory. So classical physics was wrong, not so wrong, but these are the initial observations of. It's not totally wrong, we can say, but that was started with that concepts only. We started studying the atoms. Next, coming to the Planck's. Actually, what you studied in the atomic structure, first you studied about the Rutherford, then you studied about the Bohr's theory. Bohr's theory. After that, you'll study about the Planck's constant equations, all those things, because Planck studies about the quantum nature of energy levels in the electrons he studied, right? So, what is easier to believe? Hundreds of years of laws and theories physics are wrong, or Rutherford classical model of the atom of our atom is wrong? Both classical physics and Rutherford's model have some flaws. We can say flaws only, but we cannot say totally wrong, because those are the initial assumptions, observations we can say. But this is our idea of the atom for the most past wrong. Okay, this you can see the Planck's for studying the energy of the atom. The Max Planck got the Nobel Prize in 1918. So energy is not a continuous stream, but consists of chunks or discrete packets. Energy is quantized, quanta flow. Electrons can only have a certain discrete amount of energy. Each energy quantum can be defined as each is equal to hf, where E is the energy of the quanta, and F is the frequency of vibration, and H is the Planck's constant. So these are the fundamentals what you studied in the Bohr's model. I think you know about the Bohr's model. The electrons revolve around the nucleus, and electrons are negatively charged particle, and nucleus contains protons and neutrons. Proton is a positive charged particle, and neutrons are the no charge particle. So I'm going a little bit in depth from the basics. So we'll see what is energy bands. So these are all related to the forces acting on the electrons, centripetal force and Newton. Centripetal force is equal. Then I see, if you see the electron, the concepts of the Bohr's model, an electron in an atom moves in circular orbits around the nucleus. If m is the mass, v is the velocity, and e is the charge of the electron, then the acceleration of the electron is the a is equal to v square by r, and the force and electric static force F is equal to k square by r, so k is a constant. These are the basic fundamentals what you study. Only certain circular orbits are allowed, but this is just starting point. These are all basic fundamentals related to the atomic structure. Now here you can see in the atom, you'll find the orbitals based on the atomic number. So each, if you say any shows is nothing but the number of the orbital, the electrons or revolves around the nucleus in orbits, right? So n is into every atom will have different types of different number of orbits based on their atomic number. So each orbit will have some energy level. So the electrons move from one orbit to another orbit. If the electrons jumps from higher orbit to the lower orbit, then an electron releases the energy. When the electron moves from lower energy level to the higher energy level, the energy it gains and moves upside. So these are all related to the energies. I'm going right. This is a very, very important energy. So in the atoms, when the many atoms are clubbed together, combined together, then we can find the energy bands. As I told you already just now, each orbit will have some energy levels, some discrete energy levels. So when you combine more number of atoms, you'll find the discrete energy bands. If you see this slide content, the magnitude of the influence of neighboring atom depends on the type of atoms. That is, the number of electrons in atomic shell and protons in nuclei, the environment of each atom, and also on location the electron within the group of atom. In accordance with the Pauli's exclusion principle, when a system consists of many identical atoms, that's what, when the material consists of many number of atoms, the individual energy levels of the electrons of individual atom turns into energy bands. So when you combine the atoms and when you group an atom, number of atoms, the energy levels of each atom will form a band, energy band, right? Energy band. An energy band is an energy range with many allowed adjacent energy levels very close to each other. So in the system, we'll see conduction band and valency band. In the valency band, we'll find the electrons. In the conduction band, we don't have the electrons. Here you can see, based on the atomic spacing, you can see the energy, right? So this we'll see, right? So when the length of the particle is reduced to the same order as the wave packet, just now we studied in the atomic structure concepts, wave packet, and then the quantum confinement effects occurs and the material properties modified. So material property changes when this is called actually confinement of atom sizes. So quantum confinement effects also we can say. So when the size, when there is a variation in the sizes of nanomaterials, then the properties also changes. Depending on the dimension of the confinement, three kinds of confined structures are defined. One is quantum well, quantum wire, and quantum dot. So quantum well is nothing but it's a three-dimensional object, and quantum dot is a zero-dimensional, and quantum wire is a one-dimensional, and quantum well is a two-dimensional. Right. So the reduction in dimensionality caused by confinement of electron from bulk 3D to a thin crystal layer 2D leads to a sharp change in the behavior and transformation of degree of states. This is very important. Degree of state. Degree of state is nothing but number of energy levels by the amount of energy. This is very, very important. What is the reason for special properties of nanoscale material? This is very, very important. Now, why these nano materials are having very good properties? Because they will have the high surface area volume ratio. This is because of the surface high surface volume ratio. These nano materials are getting very special properties. Now, if you see this concept, surface to volume ratio, if you see this cube, the cube area is having 6 faces, and each length is 1. Then the area is coming under 6 centimeters, right? Area 6 centimeters. When you divide this into 8 parts, then its area is becoming 12 centimeters square. When you divide this into how many parts? 27 parts, then it is coming under 18 centimeters square. 1, 2, 3, 6, 9, 9, 3, 27. Okay, 27 parts, it's the area. So when you divide the material into small blocks or small particles, the surface area is increasing. Volume is same, but the surface exposure area is increasing. So this surface volume ratio increases. When surface volume ratio increases, then definitely the material properties will increase, will change drastically. So that is this is the main concept behind the special properties of nanoscale materials. This is, for example, if you see the surface energy or surface tension, we call surface tension effect, or we can say surface energy. This nanomaterial will have high surface energy. Why? Because I think you might be knowing the surface tension effect in the fluid mechanics. So same concept applicable here. The larger the sample, the smaller are the fraction of atoms on the surface. Okay, when the size of the atom, when the size of the particle is very high, then the fraction of atoms on the surface will be small. Atoms on the surface have few neighbors than outside atoms inside. I think all of you know the surface tension effect. Suppose if you take two particles inside the a material and the particle which is at the surface, the particle which is inside the material, that will be attracted by the neighboring atoms. So the force of attraction takes place from all sides, all directions. So it will be at equilibrium. It can the equilibrium net force will be zero when the particle is in the middle of the material or middle of the water or something, any particle. So the particle which is at the surface undergoes only undergoes the force of attraction from three sides. From the top, there is no, on the top of the particle, there is no atom. That's why it undergoes a tensile force. So a surface energy of the particle will be high, surface energy. That is called surface tension only. The surface layer has excess energy, surface free energy to the bulk melt. Reducing the particle causes increasing in its surface energy. Surface energy increases when the surface area increases, which leads to a change in properties. Coming to the size effects, as I told you already, this is very, very important. When the size changes, why the properties varies. See, at the nanoscale, the properties become dependent on the size. The chemical properties, the thermal properties, mechanical properties, optical properties, electrical, and the magnetic properties changes because of these sizes, size effects, we can say, size effects. The chemical properties, reactivity. When the size decreases, reactivity increases or not. Just best example, the Disprin tablet. You take Disprin tablet. What we do, we will if we drop a Disprin tablet in the water, immediately it dilutes and dilutes, right? So it is made up of small particles. So reaction will be very high in nano-sized particles. In what is the main use of the Disprin hospital? For the immediate effect on the problem, all right? So nowadays, this in the medical field, these nanoparticles are playing major role. Nanoparticle sized drug in the drug field, these nanoparticles are playing pharmaceutical industry, we can say. And the pharmaceutical industry, nanoparticles are playing a major role. And if you see the R&D of the Arabindo, Reddy's labs, and Matrix, you will find the many R&D equipment related to the characterization of nanoparticles and fabrication of nanoparticles, related equipment available. So much research work is going on in pharmaceutical. So the reactivity will be more if the size is in nanoscale. And also thermal properties, melting temperature. Melting temperature increases or decreases? Melting temperature decreases. Why the melting temperature decreases? When the surface area increases. When you divide the bulk material into nanomaterials, the surface area increases. Just now we have seen in the previous slide. When it is in the form of a cube, its surface area is only the 6 centimeters square. When it will divide into 8 parts, its area is becoming more. Area is becoming more. So when the surface area increases, then energy absorption will be high from the surface. So when the energy absorption is more, the melting point will decrease automatically. I think you might be understood what the concept of surface area. So melting point decreases. If you see this graph, see based on the size, when the size decreases, the melting point is decreasing because of higher surface area. The melting point is gradually decreasing from higher size to lower size, right? And also mechanical properties are increasing because of the bond between the particles. Because of the bond between the adhesion, capillary forces also increases capillary forces. And mechanical properties nowadays, because nanomaterials are playing major role in the metallic industries. For example, aerospace materials and many nanoparticles are playing major role in the composites. Okay, because of higher mechanical properties. And optical property, just now we have seen the in the history of the nanotechnology, many of them studied about the optical properties only based on the size of the particle. The absorption and scattering at light is different. So different optical properties are having based on the size of the electrical properties. See, electrical properties varies based on the energy gap in the nanomaterials, and the based on the size, the energy gap varies. When the energy gap varies, the electric conductance will vary. That is the major concept in the semiconductors design. So electrical properties also varies when the size changes, and the magnetic properties also changes when the size changes. When the size decreases, magnetic properties also increases. So if you see the content of this slide, the melting point is the temperature at which the atom in a substance have sufficient energy to overcome the internal atomic forces that hold them and fix the position in a solid. On a scale of macroscopic length, the melting point material does not depend on size. Both ice cube and glacier melt on the same temperature. See, nanocrystal decreases, surface energy increases, melting point decreases. And this is the basic concept of the decrease of the melting point. Surface area increases. When the surface area increases, then surface energy also increases. Just now, we in the previous slide we studied about the surface tension and surface energy, right? When the surface energy increases, then melting point automatically decreases. So, in the melting of materials, the energy required will be low. So, for the nanomaterials, the energy required will be low to melt the nanoparticles. And heat transfer of material is carried out by two different mechanisms: lattice vibration waves and free electron size effectively observed. And the particle size becomes close to the uh, electrical free path. So this is already we discussed about this. So these are the nano structure sizes and examples for the material or applications. See, normally the semiconductor size will be, nanostructure size will be 1 to 10 nanometers, and insulator 1 to 10 nanometers. Metal nanomaterials are 1 to 10 nanometers. Magnetic materials 1 to 10 nanometers in the quantum level, quantum dots and nanocrystals and clusters. I think you know clusters, atoms, and bulk, molecules, and bulk. Okay. Ceramic oxides radius will be 1 to 100 nanometers, and nanowires will get for metals, semiconductors, oxide, fluorides, and nitrides, and their diameter will be normally 1 to 100 nanometers, and nanotubes diameter will be 1 to 100 nanometers, and the materials for the nanotubes are carbon, including fullerenes and layered chalcogenides. This is the material from adapted from J.G. Ortner and CNR of pure applied chemistry. Properties and properties. These nanomaterials will have different properties: catalytic properties, electrical properties, magnetic, mechanical, optical, spherical, biological properties. So, based on the size, when the size decreases from bulk to nano, these properties also changes. Just now, I given the um, tablet. When the nanoparticle changes, the reaction will be more, right? So the catalytic efficiency through higher surface to volume ratio. Electrical, increasing electrical conductivity in ceramics and magnetic nanocomposites. Increased electric resistance in metals because of this size. Increased in magnetic property, and particles behaves like a supermagnetic behavior. Improved hardness, toughness of metals and alloys, ductility and super elasticity of ceramic. So these properties are varying based on the size of the nanoparticles, right? Coming to the energy band, this is very important as per the semiconductors design. These energy bands plays major role. See here, I'm going to the concepts of the quantum physics. The electrons in the same orbit having different energy levels, that you know very well, because energy will varies with respect to the number of electrons. The grouping of these different energy levels known as what energy band. Then when your atoms come bring together, then when the atoms bring together, what happens? The discrete energy levels comes closer to each other, and they'll form a band. That band is nothing but what energy band. So there are three types of bands. One is valency band, conduction band, and forbidden energy gap. The energy band consisting of the energy levels of the valence electrons is known as the valency band. So as I told you already, the valency band will have the electrons based on the energy levels of the valence electrons. The valency band will have the energy. And conduction band, the energy band consisting of the energy levels of free electrons is known as the conduction band. So upper one is the conduction band, the lower one is the valency band. And forbidden energy gap. Here you can see the energy gap between the conduction band and valence band here. So forbidden energy gap is nothing but the energy gap between the valence band and the conduction band. The energy difference between the valency band and the conduction band is known as the band gap. So what is the band gap? The energy difference between the valency band and the conduction band is known as the band gap. Okay. So due to this band gap, material can be divided into three types. This is very important. Due to the energy gap or band gap, the materials are classified into three categories. One is conductor, semiconductor, and insulator. The conductors, the valence bond and conduction band overlap each other. The first metal figure you can see, they are overlapping each other. The conduction band and valency band both are overlapping each other. So in semiconductors, there is a energy gap. There is a band gap between the conduction band and valency band, and you can see more gap in the insulator. So see, I'll tell you why these materials will have different optical properties. See, when the in the atom, normally the electrons move from valence to conduction, conduction to valence. So when there is a very high gap between the conduction band and valency band, when the electrons move from the conduction band, then it cannot enter into the valence band. It will fall into the energy gap. When the energy gap is more, the frequency of the electron will be different. When the frequency of the electron is different, then emission of the light will be different. So the emission of the light depends upon the frequency of the electron. So different because of the size of the nanoparticle, the energy varies. Sorry, the color, the emitted color will be different. So now if you see the decrease in nanocrystal size or crystal size, bulk semiconductor, nanocrystal semiconductor, molecule. When you move from bulk semiconductor to the nanocrystal semiconductor, the energy gap is increasing. Because of this energy gap only, the properties are varying. The size of the nanoparticles decreases from left to right, and the corresponding increase in the band gap is reflected in the change in the color of the photoluminescence from red to violet. Because of this band gap only, the colors are changing, optical properties are changing in the nanoscale particle. Now, coming to the quantum dots. Quantum dots, as I told you, it's a zero-dimensional nanoparticle. The quantum dots are fragments of semiconductors with a bulk bond geometry with surface states eliminated by enclosing a material that has larger band gaps. So these quantum dots will have more band gaps. Because of that, they will emit different colors. So these quantum dots majorly used in the screens, LED screens, in the monitors, computer monitors, TVs. As you know, Because of this quantum dots concept only, we got uh, different types of LEDs. Quantum dots contains 100 to 1000 electrons and are 2 to 10 nanometers in diameter and 2 to 10 to 50 atoms. Changing the band gap of semiconductors is the most attractive due to fundamental technology importance. Widely tunable band gap semiconductors are considerable materials for new generation flat panel display photovoltaic, optoelectronic devices, lasers, sensors, photon bandgap devices. You can see the application of these quantum dots. So in these optoelectronic devices, lasers, sensors, and photon bandgap devices, these quantum dots are used. You can see the images of the quantum dots here. These images allow us to visualize the different geometry of quantum dots as nanoparticles. Single molecule self-assembled image, you can see lateral quantum dots, you can see nanotube in the form of quantum size. At the same time, quantum dots can be considered as structure from molecule to devices. So quantum dots can be considered as a structure. It can be a molecule or it can be a device. You see the devices, nano devices are coming, right? So these are quantum. Now you can see the applications of quantum dots. Quantum dots applications you can use in the light emitting diodes, photoconductors and photodetectors, photovoltaic cells, and the biomedicine environmental applications and catalysis and others. So these are the many applications the quantum dots are used in the nanotechnology, or now we can say nanoscience, we can say. Actually, this is also a very important concept in the nanotechnology. See how we'll make the bulk material into nanoparticles. That is very good. We follow the two approaches to make the bulk material into nanoparticles. One is top-down approach, another one is bottom-up approach. These are the two important approaches we follow to make the bulk materials into nanoparticles. Okay. Now, if you see the top-down approach, the bulk material we divide into powders, then the powders are again divided into nanoparticles. So we are moving from bulk material to small particle. That is top-down approach. So dividing, there are many technologies in the top-down approaches, and also many technologies are available. Techniques, so we can say techniques available in the bottom-up approaches. But there are some flaws in the top down approaches. That's why nowadays no one is using the top down approaches. When you divide the bulk material into nanoparticles, the particles are losing their properties because of external forces acting on the body and some other problems. The nanoparticles are losing their properties. Because of that, now nobody is using the top-down approaches. Everyone is going for this bottom-up approach. In the bottom-up approach, the group of atoms will be made into clusters. Then the clusters will be made into the nanoparticles. As you know, the atom sizes are more than in nanometers only, but the size will be more. Then atoms, a group of atoms, they'll make into clusters, and the cluster the atoms will divide into clusters, the cluster divided into nanoparticles. So quite opposite approach. Coming to the same applications, these nanomaterials has been used in many applications, biosensors, bioimaging applications, fuel cells, sensors, storage, and biomedicine, right? And anti-cancer drugs, time-released medications, gene therapy, and packaging materials also. These nanomaterials we are using. Here you can see the different fields where we are using the nanomaterials: biomedical, healthcare, construction materials, electronic and energy storage, environmental remediation, and food packaging, accessing processing and agriculture, and renewable energy. In these areas, these nanomaterials are used. There are many applications. It's a very vast subject, nanotechnology. these are the areas where we use the nanomaterials. Cosmetics also, we just now wear the sunscreen how to avoid the ultraviolet rays. Chemical process, composite materials, textiles also we are using surface coatings, and medicine majorly we are nanoparticles we are using in medicine to get rid of so many problems with fast recovery. To get the fast recovery, these nanoparticles are very useful. And in the packaging, composite materials are we are using electronics, displays, data memory, laser diodes, fiber optics, optical switches, filters, conductive coatings, anti-static coatings, transistors. So majorly this area, in this area, the nanoparticles or nanomaterials are used. Right. If you see the graphene, which is used in the electronic applications, this graphene, graphene is a nanoparticle. Its properties are high electrical conductivity. This graphene will have high electrical conductivity, exceptional mechanical strength, and thermal conductivity. And this graphene nanoparticles, nanomaterial, is used in many applications. Transistors in transistor applications enables faster switching speeds in field effect transistors. That's FETs. We call them FETs due to the high electron mobility. Interconnects reduces resist losses in interconnect layers in integrated circuits. And also this graphene nanomaterial used in the sensors, which sensitive to the changes in electrical and chemical environments, making them ideal for chemical and biosensors. So this graphene material used in these applications. Coming to the carbon nanotubes, carbon. I'm not able to show the carbon nanotubes images, but when you roll a graphite sheet into a cylindrical form, then a bond between takes place the two edges of the sheet. Then it will form a cylindrical tube. That tube is nothing but a carbon nanotube. It will have an excellent electrical conductivity, high aspect ratio, and high mechanical strength. The applications are logical circuits, potential replacements for silicon in transistors, offering faster performance and lower performance power consumptions. And these carbon nanotubes are also used in flexible electronics, used in bendable devices due to their mechanical flexibility. Memory devices, CNT based memory cells provides a high speed and lower power requirement. Nowadays, we are mostly using this carbon nanotube in the memory devices because of this high speed and low power requirements. The major concept is miniaturization and low power requirement for the applications. Now coming to the properties of not able to see here. Black phosphorus. It's also the nano material, black phosphorus nanoparticles. It will have higher carrier mobility and a tunable band gap. The major applications are electrode transistors, which enhances the performance in low power electronic devices, sensors, detect gas and light and biomolecules. These are some of the I'm discussing about the different types of nanomaterials where we use in the metallic and magnetic nanoparticles. They will have a very unique plasmonic and magnetic properties. And these materials are used in plasmonic devices like enhancing the light matter interaction in photonic devices. And also the spintronics, magnetic nanoparticles improve data storage, density and energy efficiency in spintronic devices. These are some of the applications of the different nanomaterials. Nanowires, quantum dot, just now we discussed it. Nanowires properties are high aspect ratios and excellent charge transport. Majorly used in the LEDs, transistors and photovoltaics. Quantum dots used in display technology. Just now I informed you, and photo detectors and lasers because of their tunable electronic and optical properties based on size. And oxide nanomaterials, they are used in transparent conducting films used in touch screens and solar cells. And in the gas sensors also we use this oxide nanoparticles detect specific gases due to changes in electrical properties, and resistive switching memory based for membristors and neuromorphic computing. These are some of the applications related to the nanomaterials. So based on the applications, we choose the material. So these are the very emerging trends in nanomaterials and nanotechnology. Neuromorphic computing, nanomaterials enables the creation of membristors and synaptic devices that mimic brain-like functionality. The nowadays see membristors and synaptic devices that mimic brain-like functionality. They'll work like a brain. Flexible and wearable electronics, advances in nanomaterials lead to foldable, stretchable devices. So we can fold in any way if the material size is very small. So see, just now, the foldable laptops screen also we can fold it. Even the mobiles also we are observing the screen can be folded into two parts or three parts. So this type of facility we can create by using the nanomaterials. And also the present trend is sustainable energy. Nanomaterials improve efficiency and reduce energy consumption in semiconductor devices. So this is the now everybody is using this word sustainable energy, sustainable energy. So these nanomaterials improve efficiency and also reduce energy consumption in semiconductor devices. So these nanomaterials, graphene nanotubes, quantum dots are majorly used in the semiconductor designs and developments. So I covered most of the nanomaterials which are used in the semiconductors, and also there are so many techniques available in the nanotechnology to manufacture or fabricate the semiconductors and electronic devices, so that you can go through the literature if you want to, if you are interested to go in depth. And also there are many techniques available in the nanotechnology to characterize the nanomaterials. I think all of you know the scanning electron microscope and atomic AFM, we call it as AFM. There are many techniques are there to characterize the nanoparticles. We call them TEM also is there, TEM of SEM. All these are, there are many are there to characterize the. So if you want to know about the techniques which are used to characterize the materials, you can go through them. So with this, I'm ending my talk on the nanomaterials and nanotechnology, but I concentrate only on the nanomaterial, but I didn't concentrate more on the nanotechnology. So nanotechnology is a big area. So it takes a lot of time if I focus on the nanotechnology. That's why I confined my talk to the nanomaterials which are used in the semiconductor designs. So the major, finally, what I want to say is because of the exceptional properties of the nanomaterials, these semiconductors are designed. So with this, my talk is I'm going to wind off. So if any queries, please let me know. And before queries, I would like to inform you one important point here. Just a minute. I don't know how many participants are there, but see, this is my latest international conference, which I'm going to organize in Mallarity Engineering College in the month of February. The topic of the international conference is the sustainable materials and manufacturing for Industry 5.0. And it is on February 21st and 22nd of 2025. Mechanical department and civil department both combinedly organizing this conference. And the publication partner for this conference is AIP, American Institute of Physics. So all the accepted papers or selected papers will be published in this conference, and the extended papers we are going to submit in the SCI and Scopus journals. So yeah, the SCI and Scopus journals are recent patents in mechanical engineering and surface letters, and also into innovation and emerging technologies. And some more journals we are adding with. Recently, we got the agreement from the degrooted journals like Journal of Mechanical Behavior of Materials, and also we got one SCI journal that is Archives of Metallurgy and Materials. If anyone of you are interested in submitting the proposal, please papers, please welcome, because I am the convener of this program, and also I am the guest editor for this conference journals, and also I'm editor for many journals like Journal of Engineering of Wiley, and also I'm editor for the Advanced Polymer Technologies of Wiley, and I'm also the editor for Springer Journal Discovery of Mechanical Engineering, and also I'm editor for recent Advanced Materials Journal, which is an degrooter. So for many journals, I'm the editorial and editorial member. So if anybody wants to publish the paper related to materials and manufacturing, they can submit the papers in this conference. So if anybody wants to specific publication, then I can help you if anybody interested. You can contact me. I'll give the mail ID to the organizers. They'll share you my mail ID. If anybody help from my side in publication, I can help you. But that's what I would like to say. Thanks for giving this opportunity, and I thank the Kiran Kumar sir for giving this opportunity, and all the organizers. Thank you, everyone.
Thank you very much for your informative session, sir. Dear participants, now the session is open for the question and answers. So if you have any kind of queries that you would like to ask the resource person, you are welcome. Sir, one of the participants, I am reading out one of the questions by the participants.
Yeah.
Maheshwari, she has asked a question in the chat box. Sir, a VLSI scholar can apply or not?
VLSI apply. See, if the content is related to the materials only, we are going to consider for this conference. We cannot consider only VLSI technology related papers for this conference. Only material based.
Okay, thank you, sir.
Sir, excuse me, sir.
Yeah, tell me, please.
Sir, excuse me, sir.
Yeah.
Sir, can you suggest me one of the best author related to nanomaterials, sir?
Best
in civil engineering. Best author related to nanomaterials in civil engineering, sir.
Best article or best author? What you are saying?
Author, sir.
Authors. Many authors are there who are working in nanomaterials in civil engineering. If you Google search, many people are there. I cannot pick any one person in the nanomaterial area. So you search the Google, you'll find many people who are working in the nanomaterials, and you write the mail to them. They'll help you in any point. It's not a big problem.
Okay.
Yeah.
Okay. Sir.
And you can visit many labs. You can visit IIT or any R&D pharma labs. You'll find many people are working on nanotechnology and nanomaterials.
My concept is on nanosilica, sir.
Nanosilica. Yeah. Many people are working in civil engineering on nanosilica because of the exceptional properties of nanosilica. You'll find many people in this area. It's not a big problem. If you just search the Google, you'll find the people. Okay, that's not it.
Okay. Thank you, sir.
Okay.
So we are concluding the session. So we are deeply grateful for your enlightening session, sir. Your expertise and insights are greatly enriched our participants, and we appreciate your time and the effort you have invested in making your session so engaging and very informative. Thank you, sir. Thank you for your valuable contribution to the program's success. Thank you, sir.
Thank you. Thank you, one and all.